Okay, in this short video, I'm going to discuss 5 questions which were asked by my students as doubts. So the first four are on electricity and magnetism, and the last one is on work energy theorem. So let's get started. The first one says that the diagram shows the path xy of an electron. So electron will be having a negative charge. So make a note of that negative charge on this. That passes through a thin foil. So now you should start wondering, why have they mentioned that it passes through a thin foil? What role does it have to play in the motion of the electron? It is placed in a vacuum, so there is no other particle in this region which can slow it down except the atoms present in the foil. So the foil is like a thin barrier through which the electron is trying to move, and it will collide with the atoms in the barrier and slow down. So that is the main point you need to apply here. Now there is a uniform magnetic field acting perpendicular to the plane of the page. So it could be either out of the page shown by this dotted circle or into the page shown by the crossed circle. Which one of the following statements best explains the path followed by the electron? Now, whichever way the electron is moving, if it is curving towards one side, that means the center of the circle is towards that side. So it's curving towards the left region. So the center of this circle lies towards the left. That means the centripetal force has to be towards the left. So now you know that the force on a moving charged particle in a magnetic field is given by the Lorentz force formula, F is equal to Q into V cross B. If Q is positive, the direction of force is same as given by the right hand cross product rule. If Q is negative, the direction of force is opposite to the answer of the right hand cross product rule. So now in the right hand cross product rule, you take your 4 fingers, keep it perpendicular to your right hand thumb, okay, and then point your 4 fingers along the V vector, and when you curl the fingers towards the B vector, the magnetic field vector, that means towards the open palm, then your right hand thumb will give the direction of the force. So in this case, you want your right hand thumb to be already pointing towards the center of the circle, which is towards the left of the screen. So if you do that, one way you can curl your fingers in the direction of magnetic field so that the right hand thumb is towards the left is if your fingers are pointing up. So if your fingers are already pointing up, that means velocity is up. But then if the thumb is already pointing towards left, that is the direction of force on a positive charge. Now you want the direction of force on a negative charge. So you have to make your right hand thumb point towards the left. So now if I make my right hand thumb point towards the left, then the charge particle is going from x to y, and magnetic field is out of the plane of the page, which is option D, then the force would be towards the left. So it right now seems option D is correct. But then let's apply the concept of the foil causing it to slow down. So if the foil is causing it to slow down, what would be the effect on its radius of curvature of the orbit or trajectory? Let us see. The force is Q into V cross B. So in this situation, velocity is perpendicular to the magnetic field. So the angle theta between velocity and magnetic field is 90 degrees. So V cross B will become BB sine theta. Sine 90 is 1. So it's just QVB. So this is the net force acting on the charged particle, of course ignoring gravitation, and this is going to supply the centripetal force of mv squared by r. So now the v will cancel out with the square, and you get r equals mv by qb. Now m, q, b, they are all constants. So r is proportional to the velocity of the particle, and we know that velocity will get reduced after crossing the foil. So r will also get reduced after crossing the foil. So in this side, the radius of curvature is, let us say, here to here. So it's part of a circle. which is very big, but in this case it's part of a circle which is quite small. So R has reduced. So that means this part is after, this part is before. So it's going from X to Y. So if it is going from X to Y, the velocity vector at the location of the foil should be up the screen. So this is the direction of velocity vector up the screen. So now use your right hand crosswalk rule. The thumb should be towards the right hand side. So if the thumb is towards the right hand side and magnetic field is out of the board, then and velocity is up the screen, then V cross B, when you do, your right hand thumb is pointing towards the right of the screen, which is the direction of force on a positive charge. So on a negative charge like the electron, it will become towards the left of the screen, so that it will provide the direction of the centripetal force towards the left, which is the correct direction of force, to make it curve towards the left. So the correct answer is direction of motion is from X to Y. So it has to be, so these two are wrong options. And then the direction of the magnetic field has to be out of the plane of the cage. So option D. So it's not option A, it's option D. Okay. Okay, now let's do the next question. So in this question, it says 4 resistors are shown. Okay, now in this, a lot of things are that explained. We will conclude it also with a simulation. So let me open the FET simulation. So if you look at the problem, you have a power supply. Let us say it is plus V volt at the positive terminal and 0 volt at the negative terminal. So this point is at plus V volt, this point is at 0 volt. And you are having two branches of resistors. They are given that R1 and R4 have 2R. So this is 2R, this is 2R. R2 and R3 have R. So this is R, this is R. And in between you just have a voltmeter which has infinite resistance. Infinite resistance means no current will pass through it. So it is basically like a disconnect. It's like an open branch. So the circuit will be simplified as you're having a section which is at V volt, and you're having a line which is at 0 volt, and you're having two parallel chains of resistors, where one is 2R, another is R, one is R, another is 2R. Okay, now let's call these midpoints between the resistors as A and B. Now current will obviously flow from higher potential to lower potential in both the branches. Now For the same potential difference, the potential drop is proportional to the resistor value. So in this case, okay, let's see A, B, and let's call this point C and this point D. So CA, the potential drop will be more than AD because resistance of CA is twice as much as AD, so the potential drop will also be twice as much as AD. Okay, so if you start from V, it will drop to a smaller value, so this will become a lower potential, VL lower potential compared to the point B. So in B the potential drop will be less, so B will be at a higher potential compared to point A. So now if I connect a voltmeter between them, the voltmeter will show a, so this will be considered as positive terminal, this will be considered as negative terminal for the voltmeter. The voltmeter will show a positive reading and will show a high potential difference between B to A. Okay. Now if we connect a resistor across B to A, then current will start flowing from B to A through that resistance and the potential drop will reduce because the effective resistance will reduce. Just imagine if I connect a conducting wire between B and A, then the resistance between B and A will become 0 and V is equal to I into R. If R becomes 0, the potential drop V will also become 0. If V equals I into R, if the effective resistance between V and A is going to become 0 or if it's going to decrease, okay, then the potential drop will also decrease. Right now voltmeter has infinite resistance. If we connect a finite resistance R across it in parallel, the effective resistance will become slightly less than R or approach the value of R compared to the infinity value. When two resistors are in parallel, the effective resistance is closest to the least, the effective resistance is less than the lowest resistance which is connected in parallel. So the total potential difference will drop. So option A is clearly wrong. You want the voltmeter reading to rise, not fall. So now you're left with these four options. So now think, you can increase the voltmeter reading by either increasing the potential at B or decreasing the potential at A. Two possibilities are there. So how can you increase the potential at B? If you decrease the effective resistance between CB, you can do that. And if you connect a resistor R in parallel to this, then effective resistance will become R by 2, which is half of each. Okay, so then the potential drop across CB will decrease, so B will become at a higher potential. So R3, so most probably option, so R3 is one correct option. And what about R2? So if you connect a resistor across R2, you lower the effective resistance across R2. That means the potential drop across this will be decreased, but the total potential drop across R1 will increase. So this point A will become a higher potential compared to the earlier scenario. No, not higher potential, sorry, lower potential. From C to A, if the potential drops more, then A will be at a lower potential compared to the earlier scenario. So the potential difference between B and A will become greater. So R2 is also correct. So option C is correct. So we can verify all this using a FET simulation also. Let me just show you quickly. we'll use 4 bulbs. Let me make it 10 ohm, 10 ohm, 5 ohm, 5 ohm. So these two are R and these two are 2R. Now I will connect them. So these two are the junctions between the two bulbs in each branch, across which I can connect the voltmeter, or one more resistor and also I can connect. So this is a new resistor, extra resistor of value R. So let me make it also 5. So in my case 5 is R and 10 is 2R. So this is also R, you can connect it anywhere. Okay, the current will flow from here to here to here. Okay. Now we'll connect it to the battery. So you can see the symmetry with which the bulbs are glowing. So the two R's are glowing brightest and the R's are glowing dimmest, and they are, due to the symmetry of the situation, they are glowing with the same brightness. Now let us use a voltmeter to measure the potential difference between these 2 points. So this is supposed to be a higher potential, this is supposed to be lower potential. So I'll put the positive terminal here and the negative terminal here. So you can see it is showing a positive potential difference of 3 volts. If I were to swap it, it will show minus 3 volt. Okay, as it is happening. Okay, now our goal is to increase the potential difference between these 2 points. So we can do that by decreasing the potential difference across this bulb, which you can do by connecting it in parallel to this. You can decrease the potential difference across this bulb by reducing the resistance of that bulb when across that branch. So if you connect one more R across this, you saw that the voltage increased to 4.2 volts as predicted. So interesting thing to note here is voltage increased, but the brightness decreased. Okay. Now similarly, if you connect this bulb across this bulb, again the voltmeter reading should increase. So let's test that, and it will increase by the same amount. See, again it increased to 4.2 volt. So both R3 and R2 are correct options, no doubt about that. Now let us see what happens to the voltmeter reading if we connect the bulb in parallel to the voltmeter. So this junction is fine. So it reduced to 1.29 volt. So that's because current is now flowing through the bulb, and so the effective resistance between this junction has decreased from infinity, and so the potential drop is also decreasing. Okay, I hope it is clear now. So let's move on to the next problem. The circuit shown the ammeter registers zero current. So this is called a Wheatstone network, and if the ammeter shows zero current, that means the point A and B are at same potential. Potential difference between them is zero. Ammeter has zero resistance. So when you have zero potential difference between 2 points, no current will flow between those 2 points. So A and B are at the same potential. That's the conclusion. The resistance R has a value of how much they're asking. So let's start with labeling this as point B, and this is point, okay, this is already B. So let's label this C. And let's label this D. So potential at C, let us call it VC. Potential at D, let us call it VD. Potential at A is VA, which is, let us call it V. Potential at B is VB, let's call it V. Or let's call it, okay, then let it be just V, okay. So now the potential, so as you go along the branch from C to A to D, or C to B to D, the total potential drop will be same. Finally, you are starting with potential Vc and ending with potential Vd. And in between the potential Va is same. So what kind of equation can you write? The potential drop okay, let's say you have a current which splits at junction C into, let us call it I1, and here it splits as I2. After reaching the point A, the current does not go through the ammeter because there is no current in the ammeter. So the same current will flow through AD also. So it will also be I1. And again the same current will flow through BD. The current I2 will continue to flow through BD also. And then they will again meet at junction D and become I1 plus I2. So here you have I1 plus I2. And here also you have I1 plus I2. Okay. Now potential drop across this resistor R is going to be by Ohm's law V equals IR, so I1 into R. So we are going to use the assumption that potential drop from C to D through either branch is the same. So potential drop delta V from C to D is same along both branches. Implies, okay, so potential drop from C to A is I1R plus potential drop from A to D is again I14 is going to be equal to potential drop from C to B is I2 into 2 plus potential drop from B to D is I2 into 8. Okay. Now we are having two unknowns as I1 and I2, but we are having only one equation. So we need one more equation, and that one more equation is going to be obtained by saying that the potential at A and B are supposed to be equal. So if potential at A and B are equal, that means what? You're starting with the same potential Vc and ending with the same potential at A as well as B. That means the potential drop from C to A is equal to the potential drop from C to B. That means I1R is equal to I2 into 2. So from this you can solve for, you can eliminate, you got the second equation which you want. So you now get I1 is equal to 2I2 by R. Now that you can substitute here in this equation wherever you have I1. Okay. Or you can simplify it in another way also. You can just apply the result that okay, let's just take I1 common in both the cases. So you have I1 into R plus 4 equals I2 into 2 plus 8, which is 10. And then now you have I1 is 2I2 by R. So 2I2 by R into R plus 4 equals I2 into 10. So I2 will cancel. 2 ones are 2, 2 5s are 10. So now you have R plus 4 equals 5R. So you have 4R equals 4, implies R equals 1 ohm. So option A is correct. Okay. Now let's move on to the fourth question. An electron is moving in air at right angles to a uniform magnetic field. So again it's going towards a circle like this. So the center of the circle is somewhere here. So centripetal, so if the velocity is like this, the centripetal force is towards this side. And the electron is slowing down. We already proved in the first problem that you got that QVB equals mv squared by r. Square will cancel a v. R equals m by qb into v. So if v goes down, r goes down. So as r gets decreasing, as r decreases, it will start going into a smaller and smaller circle. So that means the direction of velocity is like this. Okay. So the force is definitely towards the center of the circle and the velocity is downwards. So and the charge is negative. So direction of motion is definitely what? It is definitely anti-clockwise. And then take your right hand, keep the 4 fingers perpendicular to the thumb, and if the force on a negative charge is supposed to be towards the right of the screen at the given point, the force on the negative charge is towards the right, that means force on the positive charge will be towards the left. So keep your open palm facing the screen so that your right hand thumb will be towards the left. So now you have to keep the fingers pointing down the screen while the right hand thumb continues pointing towards the left of the screen. Now you find that the open palm is facing away from the screen, and you can curl your fingers from downward direction to away from the screen direction, which is the direction of magnetic field, and the thumb is pointing towards the left of the screen. So for a negative charge it will be pointing towards the right of the screen. So that means the magnetic field is out of the plane of paper. So it's option D. So D is the correct answer. Now coming to the last question, last doubt. An object of mass m is sliding down. So this is mass m at constant speed. Constant speed means net force is 0. So acceleration is 0. And change in kinetic energy is 0. Because velocity is constant. During the motion it travels a distance x. So let us say this is point A, this is point B. Along the inclined plane it travels a distance x and through the vertical distance of h. Consider dynamic friction is mu. What is the total energy transferred into thermal energy? That means work done by non-conservative force, which is friction, when the object travels through a distance x. So let us say the friction was acting up the plane when the block moves down the plane. So we'll apply work done by non-conservative force is equal to change in mechanical energy, and change in mechanical energy is change in potential energy plus change in kinetic energy, and we know that change in kinetic energy is 0 in this scenario from A to B, so it's just change in potential energy. So change in potential energy is final potential energy minus initial potential energy. If you define the final potential energy at this lowest point as 0, it's an arbitrary value. You can define potential energy at any point as any value. Only the change matters. So final is 0. So initial would be, it's at a height h above it. So it will be mgh. So the change in potential energy is 0 minus mgh. So minus mgh. So this will be the work done by the non-conservative force, which is supposed to be dot product of friction and displacement x. So magnitude of friction force, if you take it to be F, so friction force is, if you think of it, so F dot displacement vector into cos theta, which is cos 180 degrees. So F into product of force into displacement x into cos 180 will be minus mg, it will be a negative number. So friction force will be some newtons, x will be some meters, cos 180 will be minus, so negative number is equal to negative number, it makes sense. So the answer is, so the magnitude of work done, what he means is total energy transferred in terms of magnitude, so that will be mgh.